BMW spent hundreds of millions of dollars engineering the most advanced performance sedan ever built. A Formula One derived V10 engine that revved to 8,250 revolutions per minute. Individual throttle bodies for each cylinder. A transmission that could shift in 65 milliseconds in its most aggressive S6 setting. It was faster than the competition, more sophisticated, and packed with technology that would not appear in other cars for years. 5 years later, BMW killed it and moved on to turbocharged V8 engines. They never built another V10. They never tried to fix the problems. They just walked away. The question is not why the E60 M5 failed. The question is what went so wrong during development that BMW's engineers built a car that was fundamentally incompatible with the real world. This is the story of what happens when motorsport ambition collides with the laws of physics, and why the most technically advanced M5 ever made became the most fragile. BMW returned to Formula One in 2000 as an engine supplier to Williams Racing. The technical regulations of that era mandated 3-liter V10 engines, the most complex and high-revving power plants in motorsport. Corporate management saw an opportunity. The Formula One program carried immense marketing capital, and they wanted a road car that could claim a direct lineage to the track. The S85 engine in the M5 and the P84-5 engine in the Williams F27 shared no actual parts. They could not. The race engine displaced 3 liters and revved past 19,000 revolutions per minute. The road engine displaced 5 liters and topped out at 8,250 revolutions per minute. But they shared a philosophy. Both were designed to make power through rotational speed rather than forced induction. That 8,250 revolutions per minute redline was stratospheric for a 5-liter engine in 2005. Most V8 engines of the era peaked around 6,500 revolutions per minute. The decision to chase that kind of rotational speed was not made in isolation. Engineers faced a fundamental challenge. Mercedes and Audi were using superchargers and turbochargers to make torque accessible at low speeds. The E55 AMG delivered 516 pound-feet of torque at just 2,650 revolutions per minute. It felt like a freight train from a stoplight. BMW viewed forced induction as a dilution of throttle response and engineering purity. The brand's identity was tied to naturally aspirated linearity. The throttle pedal was not just an on-off switch for boost pressure, it was a direct mechanical link to the engine's breathing. To compete without turbos, they needed an engine that could spin fast enough to generate over 500 horsepower from atmospheric pressure alone. The decision to pursue this path would dictate every subsequent engineering choice. Bearing clearances had to be microscopic to survive the centrifugal forces. Oil viscosity had to be extreme to maintain film strength at high temperatures. The valvetrain had to be light enough to follow the camshaft lobes without floating. Every component was pushed to the absolute limit of what materials science could deliver in a mass production context. This was not about building the fastest car. Mercedes had already won that battle with the supercharged AMG. This was about preserving a specific experience, a connection between driver and machine that was rapidly disappearing. The throttle had to respond instantly. The engine had to reward the driver who kept it above 5,000 revolutions per minute. The gearbox had to shift with the violence of a race car, not the smoothness of a luxury sedan. The Formula One connection justified the V10 layout to shareholders and customers alike. It created a narrative that allowed engineers to pursue solutions that made no financial sense. A dedicated engine block with no shared architecture. Individual throttle bodies for each cylinder. A quasi-dry sump oiling system with electric scavenge pumps. These decisions added cost and complexity, but they were necessary to deliver the experience BMW demanded. That Formula One philosophy created an engine unlike anything BMW had built before. It was a monument to a specific moment in automotive history, when a major manufacturer could still prioritize the sheer thrill of internal combustion over efficiency, connectivity, or ease of use. The regulations had not yet forced downsizing. The customers had not yet demanded electric assistance. The engineers were free to build something extraordinary, even if it would be fragile. But fragile does not fully capture what was coming. The engineers had built a ticking time bomb into the heart of the engine, and they knew it. The question was not if it would fail. The question was when. The S85 V10 was a bedplate crankcase design. The entire lower section was a single massive aluminum casting. This rigid ladder frame prevented the main bearing caps from walking or fretting under the immense loads of 8,000 revolutions per minute operation. In a conventional deep skirt block, individual bearing caps are bolted into the block. At extreme rotational speeds, those caps can shift microscopically, creating vibration and accelerated wear. The bed plate eliminated that risk by making the entire lower crankcase one continuous structure with integral iron inserts for the main bearings. The crankcase itself was cast from a hyper-eutectic aluminum silicon alloy called Alusil. This material provided a hard, wear-resistant cylinder bore surface without the need for heavy iron liners. The silicon particles in the alloy created a surface that could withstand piston ring friction at high speeds while keeping weight down. Weight mattered because the engine had to sit far enough back in the chassis to maintain the 50-50 weight distribution BMW demanded. Alusil helped keep mass low while preserving durability. The engine used individual throttle bodies, 10 electronically controlled butterflies, one for each cylinder. This eliminated intake manifold volume, ensuring instantaneous throttle response with zero lag. When the driver pressed the accelerator, air reached the combustion chamber immediately. There was no plenum to fill, no runner volume to overcome. The throttle pedal felt like a direct mechanical link to the engine breathing, even though it was entirely electronic. Individual throttle bodies made the response feel immediate. BMW omitted their Valvetronic variable valve lift system because the additional reciprocating mass would have limited the redline. Valvetronic uses an eccentric shaft to vary how far the intake valves open, reducing pumping losses at part throttle. The hardware is elegant, but it adds weight to the valve train. At 8,250 revolutions per minute, the valves are opening and closing 137 times per second. Any additional mass increases the risk of valve float, where the valve spring cannot keep the valve following the camshaft lobe. The engineers chose to sacrifice part throttle efficiency for the ability to rev freely. Redline was the priority. The lubrication system was a quasi-dry sump arrangement with two electrically operated scavenging pumps. High-performance cornering generates lateral forces that cause oil to slosh away from the pickup. In a standard wet sump, this can lead to oil starvation and bearing damage within seconds. The scavenge pumps actively retrieved oil during hard driving, pulling it from the cylinder heads and the outer reaches of the oil pan, then returning it to the main sump. This ensured the mechanical oil pump always had a supply, even under sustained cornering loads exceeding 1.3 G. The most esoteric decision was the ionic current control system for knock detection. Traditional knock sensors are piezoelectric microphones that listen for detonation, but in a V10 at 8,250 revolutions per minute, background mechanical noise drowns out the signal. The valvetrain clatter, the gear whine, the exhaust pulses create a cacophony that makes acoustic sensing unreliable. BM used the spark plugs themselves as sensors, measuring the ionic current in the combustion chamber immediately after ignition. When fuel burns, it creates ions that make the gas conductive. By applying a low voltage across the spark plug gap and measuring the current flow, the engine control unit could determine cylinder pressure and combustion quality in real time. This allowed engineers to run the engine at a 12:1 compression ratio and aggressive ignition timing without the safety buffer required by acoustic sensors. They were operating at the absolute edge of what the fuel could tolerate. The connecting rod bearings operated with clearances of 0.001 inches, significantly tighter than the 0.0025-inch standard. To protect these bearings under high shear loads, BMW specified Castrol TWS 10W60, a racing-grade oil with extreme viscosity. The thick oil struggled to flow into the microscopic bearing gap during cold starts, creating accelerated wear and boundary lubrication conditions. This engineering choice prioritized high-temperature film strength for track use over cold start protection for daily driving. So, why would engineers knowingly choose an oil specification that would slowly destroy the engine from the inside out? The answer reveals everything about what BMW prioritized and what they were willing to sacrifice. The primary transmission was the 7-speed SMG3, a single-clutch automated manual gearbox. This was not a dual-clutch transmission or a torque converter automatic. It was a conventional manual with electro-hydraulic actuators replacing the clutch pedal and gear lever. Internally, it had shift forks and synchros, just like the manual transmission in a 1990s 3 Series. The difference was that hydraulic rams controlled by a computer did the work. In 2004, dual-clutch transmissions were too heavy and could not handle the torque and revolutions per minute of the V10. A torque converter would have sapped power and dulled the throttle response BMW demanded. The single-clutch SMG was lightweight and offered a direct mechanical connection between engine and wheels. The SMG offered drive logic with 11 distinct shift programs, 5 in drive mode and 6 in sequential mode. In the most aggressive S6 setting, gear changes took 65 milliseconds. That shift speed was comparable to the Formula One cars of the era, but it came at a cost. The system relied on a high-pressure hydraulic pump operating at 80 bar, driven by an electric motor. The pump's high cycle rate, combined with heat from the V10 exhaust located nearby, placed immense stress on the motor. In stop-and-go traffic, the transmission was notoriously jerky, exhibiting hesitation and clunkiness. The clutch engagement point was managed by software trying to predict driver intent. At low speeds, the system struggled. It would slip the clutch too much, causing it to overheat, or it would engage too abruptly, jolting the car forward. The experience was frustrating for anyone expecting the seamless operation of a torque converter automatic. The North American market demanded a traditional manual transmission, and BMW acquiesced in late 2006. The 6-speed manual was an afterthought, adapted from the V85 series with longer gear ratios. This caused the engine to drop out of its narrow power band during upshifts, reducing acceleration compared to the SMG. The S85 made peak torque at 6,100 RPM. With the 6 speeds tall ratios, a shift from second to third would drop the revs below 4,500, forcing the driver to wait for the engine to climb back into its power band. Manual transmission cars initially could not fully disable the stability control. Engineers feared shock loads from dumping the clutch would destroy the differential. The rear differential used a clutch-type limited slip, and the half shafts were designed for the modulated engagement of the SLMG. A driver launching the car with a manual clutch dump could generate shock loads the drivetrain was not engineered to withstand. Enthusiasts were outraged that an M car would not let them take full control. BMW released a software update in 2007, allowing full deactivation of DSC, the stability control system, provided drivers accepted the risk of mechanical damage. The update came with a warning in the service bulletin: use at your own risk. The drivetrain warranty would not cover failures resulting from aggressive manual clutch engagement. The SMG versus manual debate defined the ownership experience. The SMG was faster, more advanced, and aligned with BMW's vision of the car as a technological showcase. But it was fragile and frustrating in daily use. The manual was slower, less sophisticated, and compromised by gear ratios that did not suit the engine. But it gave the driver complete control, even if that control came with the threat of expensive repairs. There was a third option that solved many of these compromises, but BMW deliberately kept it out of North American hands. E60 M5 Touring. Only 1,025 units were ever built, all destined for European markets. The forbidden wagon that enthusiasts would spend the next 2 decades trying to import. To offset the weight of the massive V10 engine, BMW introduced GRAV construction. GRAV stands for Gewichtsreduzierter Aluminium-Vorderwagen, and it means a weight-reduced aluminum front end. The entire front section from the A-pillar forward was aluminum. The passenger cell and rear structure remained high-strength steel, creating a hybrid unibody. This was critical for achieving the ideal 50-50 weight distribution. The S85 engine weighed significantly more than the V8 it replaced. Without the aluminum front end, the car would have been nose-heavy, compromising turn-in response and high-speed stability. The weight savings from aluminum allowed engineers to position the engine further back in the chassis, moving mass toward the center of the car. Joining aluminum to steel presented significant metallurgical challenges. Conventional welding was impossible due to different melting points. Steel melts at 2,500 degrees Fahrenheit. Aluminum melts at 1,200 degrees Fahrenheit. Attempting to weld them together results in the aluminum liquefying before the steel reaches welding temperature. There is also the risk of galvanic corrosion, where the steel causes the aluminum to corrode rapidly when moisture is present. BMW developed a process using punch riveting and structural bonding adhesives. The aluminum front end was glued and riveted to the steel firewall. The adhesive was a two-part epoxy that cured at elevated temperatures during the assembly process. The rivets provided mechanical clamping force while the adhesive cured, then served as backup load paths once the bond was complete. The process required precise surface preparation. Any contamination, oil residue, or steel dust would compromise the bond strength. While successful in reducing weight, this decision had profound implications for long-term repairability. Collision damage to the front structural rails could not be repaired by traditional welding. It required specialized body shops with clean rooms to prevent steel dust from contaminating aluminum parts. The repair process involved cutting away damaged sections, preparing the surfaces with abrasive pads and chemical treatments, then bonding and riveting new aluminum panels in place. Minor structural impacts that would be repairable on a steel car often resulted in E60 M5s being declared totals. Insurance companies calculated the cost of the specialized repair against the vehicle's market value. When the repair estimate exceeded 70% of the car's worth, they totaled it. This threshold was reached quickly on E60 M5s due to the labor-intensive nature of grav repairs and the scarcity of certified shops. The electronic damper control system prioritized turn-in sharpness and high-speed stability over ride comfort. The dampers used electromagnetic valves to adjust compression and rebound damping in real time. The system could stiffen the suspension in milliseconds when it detected aggressive steering inputs or high lateral loads. On smooth roads at high speeds, the car felt planted and precise. On broken pavement at low speeds, it felt harsh and unforgiving. Engineers assumed the owner would be a knowledgeable enthusiast who understood mechanical empathy. The car required a disciplined warm-up procedure enforced by a variable redline on the tachometer. When the oil was cold, the redline dropped to 5,000 revolutions per minute. As the oil temperature climbed, the redline gradually rose to its full 8,250 revolutions per minute. This was not a suggestion. It was a mechanical necessity to protect the tight bearing clearances. The car was not designed for the appliance consumer who expected effortless operation. The friction between engineering ambition and the materials available in 2005 created specific, predictable failures that would define the ownership experience for years to come. Yet somehow, a legendary racing driver would prove the car was actually indestructible, completing over 20,000 laps of the most punishing racetrack on Earth in an E60 M5. How that is possible when thousands of owners watched their engines self-destruct is the paradox that defines this car's legacy. The throttle actuators used plastic composite gears to reduce noise and cost. Each actuator controlled 5 of the 10 individual throttle bodies through a series of linkage rods. The gears were manufactured from PPA, a glass fiber-filled plastic that worked well in low-stress applications. The high vibration, high heat environment of the V-Valley, combined with strong throttle body return springs, caused the plastic teeth to wear down over time. The gears developed play. The actuator would command a specific throttle position, but the worn teeth could not maintain it. The ECU detected variance between commanded and actual throttle position. The car entered limp mode with reduced power, throwing codes 2B15 or 2B16. This was a classic example of cost-cutting on a minor component compromising the reliability of a flagship engine. The actuators sat deep in the V-Valley, requiring significant disassembly to access. Labor costs for the repair often exceeded the cost of the parts themselves. The SAMG hydraulic pump relied on a brushed DC motor to pressurize the fluid. Carbon brushes transferred electrical current to the rotating armature. Over time, the brushes wore down from the constant cycling. The hydraulic accumulator, a nitrogen-charged pressure vessel designed to reduce pump cycling, would gradually lose its charge. When either component failed and the pump could not build sufficient pressure to the required 80 bar, the car would refuse to start or drop out of gear while driving. The transmission would display a fault message, and the gear selector would become unresponsive. This was often misdiagnosed as a transmission failure when it was actually an ancillary pump issue. The pump itself cost around $1,200. The labor to replace it added another $1,000. Many owners, faced with a quote exceeding $2,000 for what appeared to be a transmission problem, simply walked away from their cars. Salvage yards filled with E60 M5s that had nothing wrong with the actual gearbox. The rod bearing clearances and 1060 motor oil created the tolerance stacking paradox. Protection at high temperature meant accelerated wear at cold start. The bearings became a consumable maintenance item, requiring replacement every 60,000 to 80,000 miles. The symptoms were subtle at first, a slight ticking noise on cold starts that disappeared once the oil warmed up. As wear progressed, the noise persisted longer. Eventually, metal fragments would appear in the oil, visible during oil changes as a metallic sheen or small flakes on the drain plug magnet. Bearing replacement required removing the engine from the car. The subframe had to come out to access the oil pan. Once the pan was off, the crankshaft had to be removed to access the bearings. Total labor time exceeded 30 hours. The repair cost between $8,000 and $12,000 at a dealer, depending on whether the crankshaft needed machining. Independent specialists could do it for less, but it remained an expensive maintenance item that most luxury car buyers never anticipated. Launch control was included to mimic a race start, but repeated use rapidly destroyed the single clutch. The activation sequence was intentionally complex to prevent accidental engagement. The system would hold the engine at 4,000 revolutions per minute, then dump the clutch with modulated slip to provide optimal acceleration. The clutch disc operated at temperatures exceeding 600 degrees during a launch. After 10 to 15 launches, the friction material would glaze over, reducing its ability to transfer torque. Replacement required removing the transmission, a 15-hour job. Production ended in 2010, marking the extinction of the V10 engine in BMW's lineup. The successor, the F10 M5, used a twin-turbocharged V8, and the reason was environmental regulations. Euro 5 and Euro 6 emissions standards has made high-revving, large displacement engines economically unviable. High-revving engines have large combustion chamber surface areas, leading to heat losses. To cool the cylinders at high load, the engine control unit must inject excess fuel, increasing hydrocarbon emissions. The V10 produced 344 grams of carbon dioxide per kilometer. To meet fleet average targets, BMW had to downsize and use turbocharging. Turbochargers allow smaller displacement and better efficiency during official test cycles, which rarely utilize high boost. The physics were unforgiving. A naturally aspirated engine makes power by moving large volumes of air through the cylinders. The faster it spins, the more air it moves, the more power it makes. But that spinning creates friction, heat, and pumping losses. At 8,250 revolutions per minute, the pistons are traveling up and down 275 times per second. The valves are opening and closing at the same rate. The energy required just to overcome internal friction becomes substantial. Turbocharged engines make power differently. They compress the air before it enters the cylinders, packing more oxygen into each combustion event. This allows a smaller engine to produce the same power as a larger naturally aspirated unit. During the emissions test cycle, which involves gentle acceleration and steady-state cruising, the turbochargers barely spool. The engine operates as a small, efficient motor. Only when the driver demands full power do the turbochargers build boost, and by then the emissions test is over. The F10 M5 was faster and more efficient, but it was widely criticized for losing the soul of the M5. It piped synthetic engine noise through the speakers to mask the muted sound of the turbochargers. Active Sound Design used the audio system to play pre-recorded engine samples that corresponded to throttle position and engine speed. The sound was convincing to casual observers, but enthusiasts could tell immediately. There was no intake roar, no mechanical rasp, no resonance that changed with engine speed, just processed audio, piped through the door speakers. The E60 M5 stands as the final analog M5, where the sound was pure intake and exhaust resonance, not digital synthesis. The car's durability reputation was paradoxically bolstered by the legendary Nürburgring Ring taxi. For years, a fleet of E60 M5s, piloted by Sabine Schmitz, ferried passengers around the green hell. Schmitz estimated she completed over 20,000 laps in the M5. The fact that these cars survived such sustained abuse proved the chassis and engine block were fundamentally robust, even if the ancillaries were consumable. The aftermarket solved what BMW could not. Companies developed rod bearings with wider clearances and harder materials. Rebuilders offered throttle actuators with metal gears, permanently fixing the plastic wear issue. Enthusiasts developed kits to swap the 6-speed manual into SMG cars or adapt the DCT from the later M3. The E60 M5 survives today because the community refused to let it die. The E60 M5 was the last time a major manufacturer built a V10 sedan that revved to 8,250 revolutions per minute, prioritizing the sheer thrill of internal combustion over efficiency or ease of use. Subscribe if you remember when cars had souls, not software updates.